So in this learning module, we'll look at the three different ways in which we can describe vectors in three dimensions. We'll begin by looking at rectangular form, where we express the vector as a linear combination of basis vectors, much as in the same way that we did for 2 dimensions in the prior learning module. After that, we'll look at two different polar-like approaches. Recall from 2 dimensions that when we describe a vector in polar form, we're describing its magnitude and direction. That becomes a bit more complicated in 3 dimensions because in general, in order to describe the direction of a vector, we'll need multiple angles. The first kind of approach that we'll look at is describing the vector in terms of its magnitude and angles known as the coordinate direction angles, which we'll define later in this lecture. Second is kind of more of a spherical coordinates approach that you're probably familiar with from your calculus class, where we just use a different set of angles to specify direction. And we'll look at those in a few slides. So for each of these descriptions, we're going to need various conventions. One is what we're going to define for our coordinate axes. For the new coordinate axes that we have to define what the unit vector is along the positive direction for that axis, and also kind of how our angles are measured. So the book uses the coordinate axes convention that's shown to the right. The one thing, two things to note about this. Notice that the unit vector along the z direction is denoted as k hat. It's bold-faced here, but when I write it by hand, I'll put a little hat over it. And in addition, you should know that this is referred to as a right-handed coordinate system. That's much simpler to define once we talk about the vector operation of the curl. But for now, just know if you take your right hand, you align your thumb towards the positive direction of the z-axis, and you curl your fingers in the natural direction they would go. In order to be a right-handed coordinate system, you have to define x and y such that your fingers curl from x to y. So you can kind of see if you were to swap x and y in that setup that they have to the right, your curling of your fingers would no longer satisfy that convention. So in terms of representing a vector in rectangular components, as I mentioned, we just need a new basis vector along the z direction, which we have. It's denoted as k. And one thing that I wanted to mention here is the book kind of goes back and forth with respect to what it calls the component of a vector. Oftentimes, it kind of lumps in the scaling factor with the unit vector together, as it's doing in this first definition. And sometimes it actually calls the component just the actual scaling factor. I tend to stick with that latter convention, so just know that when you hear me refer to the component of a vector, I'll also often be referring to a scalar quantity, not a vector quantity. So in terms of polar-based descriptions of vectors in 3 dimensions, the first thing we need to talk about is how you actually define the magnitude. So you can actually get into a generalized theory of this for an n-dimensional vector in linear algebra. This is kind of known as a particular type of norm, which is just a measure of length of vectors in n-dimensional space. However, in 3 dimensions, since we can still do a decent job of drawing, we can actually interpret this geometrically. So if I'm interested in finding the length of this vector according to whatever scale this is drawn to, remember as engineers, we're always trying to reduce problems into things that we already know how to do. So what we will want to do is basically make this into a stage of 2-dimensional problems. So if you notice, I can, from the tip of this vector, drop a perpendicular to the z-axis. And that defines, like always for the parallelogram rule, 2 sets of triangles. When I look at dropping this perpendicular, I kind of see the triangle which they haven't highlighted, but of course that's similar and equivalent to the triangle that they have denoted here in the blue plane. So you'll notice within this blue triangle, you have one of the side lengths is a side length that you're naturally interested in, right? It's this vertical side length, which will correspond to, sorry, my mouse is not behaving, the z component. The second side length is what we'll see more formally defined as we move to the dot product section of this chapter, is the projection of this vector into the xy plane. So the logic is naturally I can compute this magnitude, which again, remember, keep the end goal in mind. You're trying to get an expression for magnitude of A in terms of the 3 components, ax, ay, and az. Well, naturally, you can express the magnitude of A in terms of az using this blue triangle. However, that will involve a projection that's not immediately defined in terms of ax and ay. However, if you take that projection, which they're denoting as A prime here, Well, that, again, following the similar procedure of dropping a perpendicular, you can form a right triangle and relate a prime by Pythagorean's theorem to ax and ay. So a prime will be the square root of ax squared plus ay squared. That's not what you wanted, though. You wanted the magnitude of a, but remember you have the magnitude of a in terms of the square root of az squared plus a prime squared. So just substitute in your result from step 2 to step 1, and you'll see that you get this formula. The coordinate direction angles are simply a description of a planar angle between the vector and each individual coordinate axes. So of course, since you have 3 coordinate axes, you're going to have 3 coordinate direction angles, and they're going to be denoted by alpha, beta, and gamma, respectively, for the 3 axes x, y, and z. So a couple things about the convention. When you have a kind of vector living here in 3-dimensional space, and I don't know about you, but when I look at this kind of drawing, the angle that's easiest for me to see at first is this gamma, because I can easily visualize dropping a perpendicular from the tip of A to the z-axis. And you can kind of envision a plane where you have a right angle here, and an interior angle of this triangle is gamma. So I'm measuring it. When it means to be measured from the positive z-axis is, of course, it's the portion of the axis going up in the positive direction aligned with k hat, and not that going down. If I were to measure it from the negative z-axis, right, this would be a much larger angular measure. So if you think about the way that definition is defined, each of these coordinate direction angles is always going to be between 0 and 180 degrees. And the reason that they're defined that way is if it were more than 180 degrees, there would be a shorter pathway to measure it from the coordinate axes to the vector going in the other direction. So, for example, look at this gamma here. There's 2 ways I can define the angular displacement from the z-axis to this vector. This short angle, gamma, or I can go the entire other way around, 360 minus gamma. So if this eventually were to go past 180, I would just take the shorter measure in the other direction. So that's why these are always from 0 to 180. Another thing to note, because of the way that these are defined, if any of these coordinate direction angles ever exceeds 90 degrees, we know that the component of the vector in that direction would be negative. So again, there's going to be so much dropping perpendiculars here within this section, and whenever you drop that perpendicular, the way that these angles are defined, again by that shortest angle convention, the component in that right triangle that results will always be adjacent to this coordinate direction angle. And if you think back to SOHCAHTOA, the trigonometric function that relates the component to the magnitude of the vector will always be the cosine. And that's why these angles are defined in terms of cosine functions that relate the ratio of the components to the magnitude. And you've heard the term probably direction cosines before. So that's where each of these formulas are coming from. You could actually sketch kind of a two-dimensional triangle, which we'll do more in the next. I know when you hear this and just see me pointing with my mouse, if you don't understand it, it's confusing. But when we actually do some drawings in the next learning module, you will see this. But again, what we're showing here is that these direction angles can be related to the components and the magnitude for each of the 3 axes. So how do you get a unit vector? Well, we can always get a unit vector given any vector by just scaling by the magnitude. So the way that a unit vector is defined, so again, using kind of that lower case convention, you can also write a u hat here, having the subscript of a to notice that this isn't just any unit vector. So we've already talked about 3 unit vectors, I hat, j hat, and k hat. But they have convention. We know that they're directed along the 3 coordinate axes, respectively. In order to tell someone that this unit vector is directed along vector A, we use this subscript here. And if you notice, we're just taking each of the components and we're scaling it by the magnitude of the original vector. And you can kind of do a little mathematical proof and compute the magnitude of this, and you will find that the magnitude is 1. It's a good exercise to go through if you've never done it. So one of the things to note, if you look at the scaling factor of each of the components of this unit vector, and you go back to our last slide, notice that the ratio of a component to a magnitude is what we call these direction cosines, or the cosine of the direction angle. So I can take this unit vector, which just arose naturally from taking a vector and scaling it by its magnitude, and I can express it in terms of the direction cosines of those angles that we defined in the prior slide. So the one thing I wanted to mention about this is if you take this definition here of describing the unit vector, you know that its magnitude is 1. So if you compute the magnitude of it, you would just take the square root of each of these components squared, which is just going to be cos squared alpha, cos squared beta, and so on. If you square both sides, well, when you square 1, you just get 1. And when you square the square root, that will make the square root go away. So you get this expression here that relates the squares of all of the direction cosines to 1. And since you only have one equation here, you can only have one degree of freedom from an algebraic point of view. So what that means is when you kind of think of and we'll talk about the same idea for the other angular description of vectors in the next slide. When you position a vector in 3 dimensions, it's always good to form a little coordinate system with your hands. That's what I always do. And then I use my other hand, I take a finger and I envision moving the vector around in the space. Once you pick the geometrical relationship for 2 of these angles, meaning you pick the angular separation between the vector and 2 of your coordinate axes, you've already, by definition, determined the separation for the 3rd axis. So that's kind of a physical realization of this mathematical reality here, that the sum of the squares of the direction cosines equals 1. That means that you only have 1 degree of freedom. Once you have picked 2, the other one is determined. So just to kind of get back to a similar idea that we've looked at in the last 2 approaches for defining vectors, we can always express a vector using these direction cosines according to this formula. So in the first approach that we showed, we wrote the vector as a linear combination of just its components. Here we're writing it as a linear combination of its magnitude. The scaling factors are its magnitude and the direction cosines. So to me, at least, a more natural way to describe the direction of vectors in 3 dimensions is using the angles that you're familiar with from your spherical coordinate definitions. And you'll recall that those are theta and phi. Oftentimes you call this an elevation angle, which measures kind of how deflected the vector is from the vertical axis. And you call this planar alignment angle an azimuth angle. So specifically theta here, we're going to measure it in the xy plane. So it's always going to be measured from the positive x-axis using a right-handed convention. Now remember that right-handed rule convention means measured towards the y-axis. So that basically, if you think about for a specific vector, we're going to have a family of vectors that would lie anywhere kind of along a slice of that sphere. And in order to determine the particular vector for a specific azimuth theta location, we need to specify this additional angle phi. And what phi is going to do is give a measure kind of in a plane that's defined by the what we'll see later defined as the xy projection and the z component. It tells us how deflected the vector is from that vertical axis. So I kind of think of the complementary angle here. If you think about picking the length of your vector and going out along the x-axis, theta kind of tells you where to go in the xy plane, and then phi indirectly here is telling you once you get there how much to elevate up and down. So hopefully that makes sense to you. Just like the last 2 forms of expressing a vector in 3 dimensions, we can write the vector as a linear combination of the basis vectors, I hat, j hat, and k hat, where the actual component values involve those 2 spherical coordinate angles, theta and phi, using this formula here. And you don't want to necessarily memorize it. You kind of want to take the same approach that we've been taking so far, and we'll look at actually drawing by hand in the next learning module video. Specifically, if I want to find the z component of here, naturally, the way that phi is defined, I have a right triangle, right? That is a 90-degree angle there because I've dropped a perpendicular from the tip of A to the z-axis. So in this plane, notice that the z component is adjacent to this angle phi. And if I know the magnitude A, I can determine the z component is just mag A times cos phi. So that's where this z component is coming from. What would mag A times the sine of phi be? Well, it will be the projection of this vector down into the xy plane. So it's kind of that length of the vector A prime that we're showing here. again, drop a perpendicular, form a right triangle, and in terms of this angle theta, the x component will be related to the cosine of it, and the y component will be related to the sine of it. So that's where why these x and y components have two different terms in their individual magnitudes. Cosine theta and sine theta are basically taking that projection A prime and moving it along the x or y axis, and the sine of phi that is common to both terms is necessary to kind of drop this vector into the xy plane. So hopefully that made some sense to you. I know it was a lot, but I know for the beginning of this statics material, oftentimes this is review from either your physics class or your calc class. So you always learn best through examples, and that's what we'll look at in the next learning module.